Had a wonderful time today on our podcast looking at molding processes with real foundry experts. Peter Mackler and Ed Kazmarek and George Harte, all old friends, all well experienced in the industry. And we talked about some of the issues we face in trying to organize, schedule, and run the molding department in a foundry. I hope you find this to be useful and informative. I thought we could revisit and begin to try and grapple with the molding process. And I thought I would start out and hope that you got some ideas of where to go. But I remember, and George, you'll remember, Ed might remember, the big discussion we had at least 10 years ago or 15 years ago about whether creating the value by making the steel or creating the value by making the mold. And the molding guy said, yeah, if I don't make a mold, you don't sell anything. And the melting guy said, well, if I don't melt, you don't do anything. Historically, when I started, our capacities were determined by our melting capacity, but that actually goes back to the original name of steel foundries, where a steel foundry was a steel melting facility that might make mill products, forgings, and castings. And people spun off the mill products and the forgings so that we ended up just making castings as steel foundries. But as soon as I started asking people, you say your capacity is 1,000 tons a month. What's the most castings you've ever shipped in a month? And they go, 350. I say, well, I think your capacity then's 400. I don't think it's 1,000. And the numbers came down dramatically after that. So when you're managing the operation, are you centered on thinking about the molding and the schedule of the molding so that the melting department serves that? Or is the molding department there to take all the metal the melting guys already got scheduled?
We base that on capacity in each area. And for us, melting was never a restraint. We scheduled based on capacity, and that was throughout the whole operation. So if you'll remember coming through our facility later, after I got my head around the whole thing, you never saw a lot of big piles of castings anywhere.
Right.
Because piles of castings is waste. And you always want to work on the one that's at the bottom of the pile, but that's a whole nother thing. And as far as your question about the mold or the metal, I always said, if we were selling molds, that'd be a great thing. Unfortunately, not. We're selling castings.
Yes. Yeah, I think that's right. I think that's right.
I worked with a person and their statement was nothing happens until somebody sells something. So when I started in my career, this was a valid discussion, molding, melting. But after the first few years, it really became people. Very seldom did we end up running into a physical capacity. We usually ran into staffing issues before the equipment maxed out.
Wow. That's just because we identified workforce as the number one priority today, but I was going through some really old files today trying to find some stuff that we did in 1999. And I was unsuccessful, but I came across studies we had back in the early 2000s where we'd already identified staffing as the number one challenge in terms of running a steel foundry, which surprised me because I thought at that time it was really pretty common to be able to get the workforce you needed.
Well, once we went through the big downturn in the early 80s, that kind of wiped out the traditional staffing model. There was severe cutbacks, of experienced staff, a big gap in hiring new people and getting them in the pipeline. And I think that the lack of orders for many years after that disguised that the staffing was the constraint. But on those occasions where there was a business boom, it usually became staffing before running into a equipment constraint.
Yeah, I think that's right. I used to tell people, being the youngest person of that cohort, having graduated college in 1976 and had the 3 or 4 years before the market collapsed in 82, there were very few people younger than me that survived because the new guy got canned because you didn't need him. And the people who were close to retirement, who cares about them? You can retire them because you don't need them and you're not going to need them for 20 years. But then you had that whole cohort of people from my age and older that stayed in the plant. And as our productivity improved, your staffing need for your base production was well satisfied. But when I would look at capacity, it was never the monuments that we had. It was never the molding system or the melting system that was a capacity constraint. You know, in a steel mill, you can say, this is our capacity constraint. If we run this 24 hours a day, 360 days a year, this is how much product we can make. In the steel foundries, that was never true. There were always small incremental capacity investments you might need to make. You might need another heat treat oven or something like that, but it was never really the equipment itself. Although that makes me think that in the molding area, that could really become a capacity constraint when business booms. So did molding ever become like the bottleneck in production?
Because we made both cores and molds on the same loop, the smaller molds. We would go at times when demand went up, we would go to a second shift, and we overcame that bottleneck that way. But we would cobble together some people who were willing to work on second shift that knew the operation well, and we would fill in other areas with people either from other areas or try and get new hires. But new hires was tough sometimes. That's how we overcame that.
I'm biased from my iron experience days, but if the operation isn't running at least 2 full shifts, that's not good enough.
Yes.
But looking at all the various constraints brings me around to another issue, which is, to me, scheduling became a key parameter for how a foundry was run.
Sure.
And so I wasn't so concerned, did the molding department set a record number of molds today? Or did melting produce one more heat that we didn't have molds to pour into anyway? For me, basically, it's a management decision. What's the schedule going to be? That's what we need for our customers. It's what properly put together sequences our operation in its most efficient way. And thus the metric is, did we hit the schedule today?
Oh, okay. Yeah. And one of the things that we touched on last week that was always a complaint I heard when I talked to the foundry operators was that the core department seemed to be neglected in the scheduling. And so they had to anticipate making cores based on the molding schedule rather than actually have a real clear line to see a line of sight in terms of what they were supposed to be making.
Well, sure. In our earlier discussion about cores, a few weeks ago, one of the issues that we brought up there was that there actually is a time limit on how long you can have cores and how much space do you need to store cores. And if you don't have a schedule and you don't have a plan, what do you have, an infinite amount of core storage space and a way to track when those cores are starting to deteriorate? And have a plan, work the plan.
So, Peter, if I have a foundry or if I'm thinking of building a foundry, what are the sort of key features of the foundry product that you need to know as somebody designing the plant? What are your 5 top questions to me when I say I want to build a steel foundry to make pumps or valves? What are your 5 different questions?
Well, you've answered 2 of them, pumps and valves and a steel foundry. So we need to know that.
Okay.
And what products are you going to make? What the range of weight, the distribution of weight, quantities in an order, short run, long run. I need to know those things.
How would you distinguish long run from short run? What would be the dividing point?
I don't think there's a single point. It's kind of a continuum. I mean, if you're going to make a 100 pieces, that's kind of a short run. If you're going to make 10,000, I'd call that a long run. I can't tell you if it's 1,500 or 2,500 is the breaking point. I don't know.
Okay.
But you know what I'm saying. Yeah.
Yep.
I wanted to get back to a couple things that we just talked about too,
Sure.
regarding what drives the foundry. The question originally was molding or pouring or melting. From my experience in all the alloys, steel traditionally, the melting was the drumbeat. Because one thing, you don't hold steel for a long period of time. When it's melted and ready, you pour it now. So that becomes the drumbeat for a logical reason, not for any other reason. It's logical that be the drumbeat. When that metal is ready to pour, you got to pour it. And now with iron, ductile iron, you can hold ductile iron overnight. I mean, you can hold it for a long time.
Sure.
So melting is no longer driving the bus, and now you've got molding that probably will drive it, along with all the ancillaries, core making, and so on. So that's been a traditional thing I've seen since the beginning of my experience. Now that we're getting more induction furnaces into steel, that's kind of changing changing this a bit. You have a few more options rather than the arc furnace. So that may modify that a little bit. So,
Yeah. One of the things that we do in the induction melting course is complain about the fact that lots of the smaller foundries that use induction furnaces treat the furnace like it's a toaster. You need a heat, we'll fire up the furnace and make a heat. And
that's not all bad, though, That is not all bad.
Well, I mean, it does give you flexibility on the one hand, but on the other hand, if you want to maximize both quality and efficiency, you want to schedule the heats in some sort of rational order so the furnace stays hot and you've got the right levels of contaminants moving forward so that you can be.
I agree. I don't think they're all mutually exclusive. But so anyway, I just wanted to touch base on that aspect.
Sure.
Where's the drumbeat? And that's the thing I try to establish when I design the foundry. What is going to be the drumbeat? You want to know what the most important piece of equipment in the foundry is?
What?
The rollover draw.
Okay.
The rollover draw. That's if you have an automated system.
Right.
If you don't roll them over, you're not going to pour them. You don't make them. So, the drumbeat of the foundry typically is the rollover draw, and you build everything around it.
One of the things that you raised, which is really fascinating, and I know that Ed had this experience. I know the people at Harrison had this experience, that in a traditional steel foundry, it still was designed as though every individual operation was an artisan operation with excess capacity and individual workstations. And so you really could go down on one machine and you still were running because you had 3 molding machines and 2 furnaces and all of that.
Right.
And then when people started buying Galante stuff, the IMF lines, all of a sudden, if one thing went down, you weren't making anything. And it really caused people, there were 2 things that it caused that I thought were really beneficial. One is it meant that if everything's not working, nothing's working. And so you had to become disciplined in manufacturing, both in maintenance and in scheduling and everything else. The other thing that was really odd, but obvious in retrospect, is you suddenly had to count cooling the casting off as part of the process because you couldn't just dump it outside if it was still hot. You couldn't handle that. So those 2 things were things, and Ed, you're shaking your head, yes, but those 2 things were things that really struck me about people when they adopted the IMF line. You had to operate all the time, and you had to have space for the castings to cool off.
Yeah, and that became a big driver in going back to my scheduling discussion, because
Sure,
that shakeout time really became a constraint.
Mm-hmm. Right.
I remember Harrison Steel put up big LED clocks that gave you the countdown until the line was going to move again. And you had, I think, 3 minutes or 4 minutes, and then the line was going to move again. And so just to get everybody on board to understand, you got 20 seconds left and this line is going to move. I thought that was a hoot. So Peter, you didn't get to finish though. How big of a do I use flask? No flask? How big of a footprint do I have for each mold? You didn't ask me how big the parting line was. You just asked me how heavy the castings were.
Well, that'll drive it. That'll drive it somewhat. The paper I'm going to present was for the TNO, deals with a chrome moly high chrome iron foundry making mill liners and mill parts that are huge.
Okay.
You know, they're 14,000 pounds up to 14,000 and so on. These are all being made in flaskless molds.
Okay.
And part of the reason is you can lay them low and they're not high in depth. In other words, you don't have a tall mold that's fairly short. So your static pressure, your metallostatic pressure isn't too great in the mold. So flaskless is not a bad deal. And we're running 2-to-1 sand to metal ratio, which is fantastic for those big molds in a flaskless mold. So if the geometry permits, I like flaskless. It's simple, a lot less hardware to move around. So you might pay a bit more for a bit more resin and sand, but maintaining flask is not cheap, and having to move flask in and out and store them, not a good thing. So I really prefer flaskless wherever possible. Now, I worked on a bomb project, which was the one that's been around 40 foundries. You've got to pour the bomb in a vertical mold, which is about 14 feet high. You've no choice but to encase that in the flask. There's just no choice. So, I mean, it depends on the geometry of the casting.
That's interesting, because my understanding was as long as I could have a couple inches of sand around the casting, I was okay. But you were saying that the head height really
Absolutely
matters.
Oh yeah, you'll blow the mold out. With 2 inches of sand and 14 feet high, you don't have a mold for more than a second. It's gone.
Wow. So how tall is tall then, Peter?
You're picking on me.
You knew I was going to ask that. Yeah.
Well, you mentioned the company in Italy, and I won't mention the name because I don't want to get into things like that, but they've had some flaskless molds where I saw that were 7 feet tall, flaskless.
Okay.
So it can be done.
So you're saying if I'm over 4 feet, I might start to get nervous.
No, I don't think so. I don't think it's that low. I'd go to 7.
Okay.
But you're going to have to put more sand and binder into it to make sure it holds together.
So George, you've done this. You use flasks.
Yes, sir. When you're putting 70 to 90 tons in a mold, you better have a flask around it. I don't care.
No debate on that, George. I would rather have a pit, frankly.
Well, we had a big pouring pit where they were in.
Sure.
And then we had big pits where we made all core assembly molds.
Yeah, exactly. And then you rammed it up with no bake around it.
Yep.
Good. Excellent. Yeah, that's good. For the huge mold, and those are huge castings. I mean, that's another league. And I've got a few foundries that do pit molding because of that fact. Just the danger of one of those things opening up and spilling all over the floor is huge. You've got to have that contained.
I've seen that happen. It's ugly.
Yeah.
I'm shocked. Something went wrong in the foundry. I'm shocked.
I think it was Ween United. You remember them?
Yes, sir.
Okay. They had actually, when I saw them, they had 3 or 4 open hearth furnaces making the steel to pour the molds. And that was in the day before big induction furnaces or arc furnaces of that size really were common. And they would tap those into this monstrous ladle of, I would guess 150 tons, 200 tons, big molds. George, you're familiar with that, I'm sure.
Yeah. So that's before 1975, though.
Yeah, I was it's probably in that range, right? Yeah.
Open hearths are gone by 1980. They're
all.
Who
knows what? Well, they had 3 or 4 of them there. Right?
The last big open hearths I know that we're running were at Blau Knox.
Yeah.
And I think they had two 200-tonners,
Mhm.
and then they had the 100-ton arc.
Yeah.
That was the last one that I'm aware of.
But Bob Shepard used to talk to me about when they closed the open hearth there at Harrison Steel. So they had one for a while. And the reason I knew the date was I graduated from college in 1976, and they forced U.S. Steel in Birmingham to close their last open hearth. The EPA did. And so that was pretty much the end of that era. So
Yeah, we had
I don't
Falk
want to.
had 3 30-tonners, and they closed those down in May of 72, and I started in June, so I never got to see those run. It was all arc furnace.
Back a few years earlier than that, I was in college in the early '60s. We went to Bethlehem Steel up in I think it was Lockport, near Buffalo, their Buffalo plant. They had put in 2 BOFs, and there were some of the early BOFs in the industry. And at that time, as I recall, the president of U.S. Steel said, "We will never, ever have a BOF." Well, what happened?
That's interesting, because one of the discussions I've had in talking to people, and I had to write a paper for a magazine about the economic conditions in the steel industry, because the talks that certainly George, you and Ed have heard me give about the history of the steel industry and the capital cycles, the 30-year capital cycles, that stuff was really popular when I did it at one of the steel meetings. So they asked me to write an article about it. And one of the things that was of concern was whether or not the steel industry could adapt rapidly enough to changes in technology. And you point out that in less than 20 years, we went from the vast majority being integrated steel mills to being the vast majority being electric arc furnaces in less than 20 years. Just almost an overnight switch, because they're worried about our ability to do it with hydrogen. And the people who run those big companies, the Nucors and Steel Dynamics and Cleveland Cliff say, sure, we can do it. It's just going to cost money. So how much do you want to pay for the steel? We can do it. It's not a problem. So Ed, you didn't weigh in on the flaskless thing, and you've been in a wide variety of circumstances. So clearly, how big does a mold have to be before you think a flask is something you really want?
Boy, I'm not going to answer that one.
I'm shocked.
Because in bigger molds, back in the day was green sand, and we've gotten away from green sand. Those were all in flasks.
Sure.
And I've seen some pretty big, what I thought were pretty big molds in chemically bonded without flasks. And I prefer that to the maximum degree possible.
Sure.
So what the limit is on the upside, on how big can you go on that, I don't have anything better to add than what Peter said, and I agree with him. And avoid the flasks if at all possible, but not every circumstance will allow that.
Okay.
I think another factor.
Our max size for flaskless was 2,000-pound pouring weight. Anything above that, we went into a flask, whether it was on the loop or on out on the molding floor.
Well, another facet to this question would be, if you're only making 12 part numbers in your entire plant ever, 12, and you decide to use flasks, it's not a bad idea, because you can really fine tune the amount of sand in those 12 castings. But if you're a jobbing shop and you're making thousands of part numbers, the flaskless is probably the best way to go, unless you absolutely have to go the other way. So I could understand if you made a few specific parts, you wanted to knock out 20 or 30% of the sand, go with the flask, and then you don't have a big problem with thousands of flasks, different sizes and all that.
Yeah, one of the flaskless questions that we ought to at least mention in passing is the alignment of the cope and the drag. So I'll give you a little bit of my understanding, and then you can correct all of my mistaken ideas. But historically, to get you lose at least a millimeter in location between the cope and the drag, typically. Something on that order, 30 thousandths of an inch or more, but that's typical. We used to use those double-sided cones, and people still use those double-sided core cones to line up the top and the bottom. I actually think there's a benefit to having an offset parting line so that you actually have the female in the drag and the male in the cope, which gives you a much more positive location. It's like printing. You actually have a right-angled corner to give you the location. And of course, it gives you a little additional safety from pouring out parting lines.
Yeah.
I think for that makes sense. And my understanding of the flash system is you depend on those pins, and depending on the pins is really a problem. So George, correct me. You didn't depend on your pins.
No, never, ever. The flask bowls from roughly 65-inch diameter to 15-foot diameter, we would use the guide cords. On the smaller stuff that we made on the loop, we would use a mold lock, as you described.
Okay.
It's very difficult, at least it was for us, to figure out how to do that on a very big flask mold. So that's why we use the guide cords.
Yeah. How much variation would you expect with your system in the big castings in terms of loss of location from cope and drag?
Well, some of that, depending upon the work and what was required, some of that work we changed to full tub. So the riser was attached to the pattern. You'd put that on the match plate, ram the whole works up, put the bottom plate on, roll it over. And when you draw it out, you got your mold cavity and your riser all in one. So all that other stuff goes away. If we were using guide cores, 13, 14, 15-foot flask, you're probably talking a half inch, maybe.
Okay.
But you would preset it. Somebody would be inside to make sure that everything lined up properly, and you could jiggle around a little bit. We call that the human guide core.
Who volunteers for that?
I used to in my younger days. It's all part of learning.
Yep.
On an automated system, Peter, you just go with some sensor array that automatically adjusts as you're closing?
No, I have not done that. I think that's in the industry, and I don't see it commonly, but it could be done. I think if you were into aerospace quality castings where you've got to just hold it so close, you'd have to use visual type closing systems. But I think it's coming, no doubt about it. There'll be more automation like that.
So Ed, you actually had that automated equipment with the automated closing. And my understanding was that was really good because you're really using a screw to line up the top and the bottom. And so you had a really precise fit between the cope and the drag. Did that work well for you? Was that?
Sure. Then you asked the relevant question. I would say it kind of worked, but we still ended up putting in some kind of column guide cores, shift lock cores, whatever. We still ended up with some system using most often something like that in parallel with it.
Just to change the subject slightly, I've made the mold. I'm not ready to close it yet because I normally put a coating on it. Now, Willie's shown that a lot of the coatings we use cause huge porosity problems, which is true because most of the coatings we use have a little bit of latex in them to give them the toughness so they don't crack. And when the coating cracks, it really does allow penetration. So they'll put a little latex in it. And that is just pure LOI. That just is gas waiting to form. So that's a problem. But most of the, especially larger molds now, use flow coating because spraying, I just change the color and I may not put enough on. And daubing, I get all kinds of variations and sometimes too thick and it cracks. So we generally do flow coating now. And it's typical to preheat before you flow coat and then dry it with thermal So you're not just waiting for it to dry out. And then you have to set the cores and close it. So is molding more labor intensive than melting? And fix what I just said about how the system works, Pete.
Whoa. Well, in terms of man hours per ton, molding is going to take more than melting. There's no doubt about it. Absolutely. Because you've got so many facets to molding. And I'm not trying to simplify melting, but I've seen a lot of melting decks with one guy up there, you know.
Sure.
So in a molding line, you've got an assembly of people trying to put it all together. Now, what was the other aspect of the question? I kind of missed that, Raymond.
Yeah, I had described the process of after you've made the mold to where you close it.
Mm-hmm.
I made a lot of assertions based on sort of my casual observations, but having never really been responsible for it the way George and Ed are, or designed it the way you did. What did I screw up? What are things that people need to know that I'm unaware of just in passing through the system?
Well, you just described the washing process, the correct washing process, which I fully agree with. And that's what I always recommend is to, if you're going to use a water base, you've got to preheat, flow coat, and then dry thoroughly. And don't be tempted to turn the temperature up on that drying oven because you can deteriorate the mold pretty quickly. And I've seen that happen where their drying ovens are just a skosh too small or short and say, well, crank it up another 30 degrees. Well, that's not a good idea. We follow the manufacturer's recommendation on that. And the other big one's viscosity, you know, the bomb A, as we call it. Yeah. Holy smokes, you can really get in trouble with that. You know, I've seen alligator skin come off after they got done with it because they didn't have the right bomb A going in. So to me that's one of the most important criteria is maintaining that bomb A.
Oh, absolutely. So let me ask you a couple of questions. One is, how hot do I preheat it, and what's a normal temperature for drying?
Well, we had an oven, but we also torched and sprayed. And if you're using water-based wash, it's simple. You give the guy 3 temple sticks, 200, a 250, and a 300. If the 200 doesn't melt, it's not hot enough because water boils at 212. It's 250 is perfect. If it's above 300, it's no good. It's too damn hot. It's not going to adhere right. And as far as the oven goes, you want to run that at a relatively low temperature, but it should be a wind tunnel. Because if you think about it, and this is something that a good friend of both of ours told me, George Vingus, if you look at a puddle of water in summer and there's no wind and it's warm out, that puddle doesn't evaporate. You get a breeze and bang, it's gone. And that is the key to drying wash with an oven. These things that I see with the little infrared lights, they ain't doing squat. You gotta have a tremendous amount of airflow.
Yes.
And we put the parameters out to a manufacturer, told them what we were trying to do, and they were an oven manufacturer, and they designed one for us in the size constraint that we had, and it worked very well. And we didn't jack up temperatures, but it was like a wind tunnel.
Raymond, you and I had a long conversation about turbulent flow and heat exchange in the quench tank. The very same thing occurs anywhere. When you have turbulent flow, you have much greater heat exchange. And that's exactly what George was saying, that you get much better heat exchange with turbulent flow as opposed to a static condition.
And you also, being a chemical engineer, are putting dry air on the surface again, rather than having air sitting there that's already wet. And so it's not taking any more water out. Your comments on bomb A really, given my lost foam background and the heavy dependence on coatings, made me think of about 4 things that people need to understand that they don't normally do. One is the characteristics of the coating, since they depend on clay, require that you have a consistent stirring action in the entire time you're using that, because if you start and stop it, you're not going to get any sort of consistency. Secondly, if you just keep modifying it, you'll run out of biocide and the bugs will get in there and it'll become bad, pretty bad. And you normally can smell that. And then there's a couple of tests that you do, which is the percent solids is really better than Bombay itself.
Yes, sir.
Yeah, once or twice, and that's George Vengus thing, as you know, George. Once or twice a day, take a sample and just do a percent solids, because that really is characteristic of it. Bombay is fundamentally a problematic measurement. So you really need to be careful to not only have the thing stirred correctly before you try and take the Bombay. You can't buy the cheap plastic Bombay gauges because they don't do very well. And your gauge R&R is pretty bad. So you've got to be pretty bad out of spec, or the guy will keep making the measurement until he gets the right number, figuring he didn't get a good measurement.
I always said Balmy was great for making beer, lousy for chicken wash. And as far as your mixing goes, that was another thing I learned from George. At least the wash that we use, the water-based wash that we use, it had long chain polymers. Because you're trying to suspend 75% zircon in water. That's tough. It's heavy. And what he told me was, if you mix that thing all day, all you're doing is shearing those polymers, and it's going to drop out of suspension. So what our practice was, tech would go out every morning, run the mixer for 15 minutes, beginning of the shift, shut it off, check the percent solids. If it was good to go until the next shift. Okay. And there was no Balmy gauges in our foundry either. I had some up in the lab as antiques, and that was the other thing. I had everything sealed up so nobody could mess with it, add, subtract. No. And eventually we started getting 300-gallon totes, stainless steel totes from the manufacturer, and those were completely sealed with their own agitation system. And when they were done, they'd go back and be completely cleaned out, checked, and come back to us. But that was it. 15 minutes at the beginning of the shift. Percent solid was good. You were good.
Wow. So Ed, you had to deal with those issues, I assume, and you never had a problem with coding, I'm sure.
Well, for the reasons we've talked about, I think coatings, wash, whatever term people want to use, they're a problem, and yet they also serve a purpose, a useful purpose. And so, okay, how do you deal with them? And we've talked about some of the equipment and a few of the tests, but I like to harp on process control and using some statistics and even big data.
Yep.
To try to track what goes on, because strange things happen. And if you don't have some kind of a system to monitor that, you can run into problems. I mean, there can be process control steps, but you still got to verify and have some kind of process control system. Yeah. And I've seen amazing things happen when you do that kind of monitoring.
Oh, I think that's right. ESCO, because they had a fairly consistent throughput, had begun to make incremental additions instead of batch type additions. And so thinking about it from a chemical engineering, material balance, energy balance sort of standpoint, it made sense that if you have a relatively consistent production, instead of letting it get to the low end of the spec and adding the material to get it back to the high end of the spec, whether it's moisture or some other additive, you could actually incrementally add it because you know what the consumption is. And then you'd still do testing to make sure you stayed in range. But most of the steel foundries seem to me to be, or more like George, where you're making batch type small lots. And there, that whole system of making incremental control is not going to be very practicable. You just can't manage that. But you might be able to, with big data, begin to do some of that kind of management. where you know how much surface area you have or how much weight you have, and so you could begin to do it. Peter did talk about, and we talked about this briefly under sand, the sand to metal ratio. What limits your sand to metal ratio? Is it really just having enough mechanical stuff around? Are you trying to control thermal? What is it that gets you up into the 4 and 5 instead of the 2?
Well, I can generalize that. I don't know that I can specifically give you one answer, but typically you have more mold just to hold it together, keep it from breaking apart. I mean, that's fundamentally the primary reason for more sand.
Okay.
But you do bring up a good point. You may have some issues for heat transfer and things like that. You may have a specific mold where you're trying to accomplish something with heat transfer. You might choose to go chromite instead of silica. Yeah, I mean, you know, there's a lot of things you can do there. So, but fundamentally, in my view, the biggest issue is just having a mold that won't come apart. It won't buckle. It won't bow. I mean, not just break up, but I mean, even if you get a little bow in the cope, you might have a scrap casting. Certainly, it'll be out of spec. So you got to make sure that whole system, your weights, your clamps, and the whole system are adequate to hold it together.
Do you see a need to modify any of the downstream sand handling, cooling processes depending on your sand to metal ratio? I mean, if you're running a really low sand to metal ratio, is that going to trigger a disproportionate need for handling in some other area?
Well, the biggest thing it'll do is give you a higher temperature sand coming through the shakeout. You're going to have hotter sand with a low sand to metal ratio. And that's probably the number one issue you have to deal with. So you're 2 to 1, you're going to have very hot sand coming out of there. And
it's the reverse. If you have a really high sand to metal ratio,
it'd be cold. Yeah, colder.
The sand will be cold, but are you going to get more lumps coming back and more binder that's got to be removed? You know,
absolutely. Yeah, absolutely. Now you've got to crush it. You've got to have probably some high energy scrubbing. You know, if you've got a low sand to metal ratio, you probably can get away with a simple shakeout, a screening unit, maybe some fluidized cooling, and you pull off some fines. And for commercial grade castings, that's probably good enough. With a high sand to metal ratio, you're going to have to go through probably a secondary high energy mechanical scrubber or thermal or both. And I recommend typically you go through from the shakeout, go through a crusher, make sure you can transport grain fine sand to your next step. But then you may have to take that and refine it. Now you can do crushers, you can do hammer mills, you can do pneumatic scrubbing, and you can refine the sand. The pneumatic scrubbing I've had experience with will have the least amount of wasted sand in terms of breaking it into pieces and sending 15% of it to the dust collector. So the pneumatic scrubbing is the gentlest, and I've had cases where we've gotten down to 0.8 LOI coming out of a pneumatic scrubber, which is great. So I'm kind of a fan of pneumatic scrubbing if you need that kind of control on LOI.
I would think that many jobbing foundries, for a variety of reasons, have greatly varying sand to metal ratios.
Yes, sir. Absolutely.
So they're going to have to be prepared to deal with those cases where it's a high sand to metal ratio.
Right.
Yeah. So what sand tests do I do at the molding level to make sure things are correct? We've talked about that briefly, or at least in passing. You know, you got to calibrate the mixer. We talked about calibration of the mixer, but what test did you do? The tensile test once a shift, once a year? What did you do to evaluate the returning sand from the reclamation? And maybe this is too complicated for the last 5 minutes, and we want to kick this down the road till next time. So we may want to do that, but what kinds of sand tests do I need to maintain the sand system so when it arrives at the molding station, I don't have problems?
I'll defer to George and Ed on that. They're the experts in that area. I have a few fundamental ideas, but these guys do it every day, okay?
Yeah.
The only thing that we did was we would run tensils, and then we would run chemical tests to make sure that everything was in the parameters to make sure that we could make a good mold. We didn't do any scratch or mold toughness or any of that stuff. No portable perms.
Whether that's the best answer or not, it's the same one I'd give. I know there's newer testing techniques that have come out to try to look at, the actual strength of formed bonded sand, and that can all be debated. But that's, a process measurement. It's not telling you what the mold's really seeing. It's the upstream, what are you doing to make sure that you've got good process control on that, the sand coming back, that you've got some kind of a way to verify what your calibration is. All those are upstream measurements. And if you've got those working properly, you should be okay.
So your upstream measurements then for your reclaim sand would be LOI and screen analysis, something like that.
Yeah.
And whatever else the binder manufacturer recommends.
Like pH.
Because different systems will require different checks, but that should all be coming out of the reclaimer. Once you're making a mold, it's too damn late.
Right. On your new sand, you've done the same kind of test.
Yes.
Okay. And then when you said you checked the chemistry, were you really talking LOI, or do you actually check the binders when they come in for chemistry?
Well, we would check percent sodium oxide because we were sodium silicate.
Okay.
If there's a way for a foundry to be checking the binder per se, I don't know what it is.
I don't know either. Yeah. That's why I asked George, and he corrected me correctly. He was sodium silicate, so he could do something.
I have never seen a foundry take the binder that's coming in and run any tests on it at all. Basically, they expect it to come as it should. And I'm sure from time to time that doesn't happen, but I've just never seen a foundry set up a chemical lab to do that.
I'm not aware of that either. I mean, sometimes I have heard of it comes in, it's the wrong color. They call the supplier and say, this is a different color. Are you sure it's right?
If you do a Pareto of what can go wrong with making a core or a mold with any binder system, the materials that you're using from a certified reputable supplier is way down at the right, and you can barely see the height of the bar.
Okay. It's a consistent problem that, Malcolm and I try to wrestle with, is that virtually all the materials we get incoming, we just trust the supplier's done a good job. The only quality control is the name on the side of the box.
I've been asked to come and help people because they got a new shipment of binder and now the molds aren't setting up. And the first question I ask is, did you open the mixer and clean it? And are the binder and hardener ports clean? And I usually get a blank stare, and you open the mixer and guess what? It's filthy and the ports are plugged up. It's got nothing to do with that total binder that just showed up.
We have previously talked about a few really spectacular failures from suppliers, but as George said, the frequency of that is really, really low.
Yeah.
And it's definitely not the first thing I would look at. And I've heard many, many times people say, oh, this stuff must be some crud we got from the supplier. And it's so easy to blame somebody else.
I think that's right. Well, that's great. Well, you guys have been great today. If you have particular questions you want to ask, or things about running the foundry, the equipment, the design, if you let me know, we'll be happy to try and dig into those deeper. Hopefully we can look forward to looking at some of the sand testing and some of the other things we do near in the future. So I hope you enjoyed it and look forward to our next time together. Thank you.